Swayam Prabha. Digital India. Educated India.
In today's lecture we will be looking at general two dimensional boundary value problems, and similar to one dimensional boundary value problem, general one dimensional boundary value problem, we will be deriving element equations. We can do that using either Rayleigh-Ridge method by coming up with equivalent functional for the given boundary value problem, or we can also derive the element equations using Galerkin criteria. Irrespective of whether we adopt Rayleigh-Ridge method or Galerkin criteria, we require to decide what kind of element we want to use for solving two dimensional boundary value problems, and accordingly we need to express the trial solution before we proceed to get the element equations. So now let us look at the problem statement. A large class of two dimensional boundary value problems is governed by a boundary value problem of the following general form. Where kx, ky, pq are some specified functions, they can be functions of spatial coordinates or they can be constants. So this is the general two dimensional boundary value problem which we require to solve over the domain A, capital A, which is an arbitrarily shaped two dimensional domain bounded by some surface S, and T is the field variable which we are after, or Tx is the desired solution. So we need to find solution of this differential equation over the domain A where A is arbitrary two dimensional domain bounded by a surface S as shown in figure here, where xy coordinates are or xy axis are indicated, and n is unit outer normal on the boundary, and this S which is the boundary of domain A on this boundary either field variable T or its derivative can be specified, and this boundary S can be divided into two parts. Let S1 be the part of boundary on which T is specified, that is field variable value is specified, and S2 is a part of boundary on which first derivative of T is specified. So if you agree for this, the two possible boundary conditions, possible boundary condition can be expressed as T is equal to T naught on the part of boundary over which T is specified, and this is essential boundary condition because order of the equation is 0th order, and if you see the second boundary condition, either this can be specified, either essential boundary condition can be specified or natural boundary condition can be specified. Natural boundary condition is the boundary condition which contains first derivative of t, and if you recall the general 2 dimensional boundary value problem that we are trying to solve is a second order differential equation. So, we require 2 boundary conditions to solve, out of which one is essential, another is natural. So, any of these boundary conditions may be specified, and where k times partial derivative of t with respect to unit outer normal to the boundary is the derivative of t in the outer surface normal direction, and is given by this one. This is how k times partial derivative of t, partial derivative of field variable with respect to unit outer normal is defined, where nx and y are components of unit outer normal to the boundary, and the unit outer normal n can be written as nxi plus nyj. So, this is the problem statement, and we are required to solve this over the domain A, which is bounded by surfaces on which either essential boundary conditions or natural boundary conditions may be specified. And if you see, or if you compare this with general 1 dimensional boundary value problem, you can see this is just an extension of 1 dimensional boundary value problem, and the finite element formulation follows same steps as before for 1 dimensional boundary value problem, with one exception. In general 1 dimensional boundary value problem, there is no choice of shape of element. All the elements that we have chosen are line elements, even though we looked at both 2 node element and 3 node element. However, in 2 dimensions there are many possibilities for element shapes, like you can have triangle, rectangle, quadrilateral, square, or triangle with curved edges and quadrilateral with curved edges, curved sides or curved edges. So, we need to look at, when we are trying to develop element equations for general 2 dimensional boundary value problem, we need to look at the possible element shapes as well. So, possible element shapes for 2D problems, the rectangular and square elements are not very useful for general applications. They can model only rectangular solution domains accurately. The triangular and quadrilateral elements are very versatile. They can model any 2 dimensional shape with straight line boundaries. Elements with curved sides are effective in accurately representing domains with curved boundaries. So, to start with, in this lecture we will derive triangular element shape functions, as triangular element is the simplest to formulate, as it is based on linear polynomial trial solutions, which will be seeing or which will be more clearer when we actually start deriving the element shape functions for triangular 3 node triangular element. So, 3 node triangular element is based on linear polynomial trial solutions in 2 dimensions. So, the required integrations for assembling the element equations are fairly simple to carry out in closed form. The quadrilateral element and element with curved boundaries are formulated using isoparametric mapping, which we will be seeing in the later lectures. So, as a part of this lecture we will be developing or we will be looking at equivalent functional for the given for the 2 dimensional boundary value problem statement that we looked at, and equivalent functional is required if finite element solution is based on Rayleigh-Grigg method. And we also look at how to derive element shape functions for 3-node triangular element. The procedure helps us to understand or to generalize it later for any noded 2D element. And also we look at the Galerkin criteria for 2 dimensional boundary value problem to derive the element equations. So, now let us look at equivalent functional for general 2 dimensional boundary value problem statement that we already noted, and before that these are the possible shapes for 2 dimensional elements: triangle, rectangle, square, quadrilateral, triangle with curved edges, quadrilateral with curved edges, curved sides or curved edges. So, equivalent functional for the boundary value problem that we already noted can be written as given here, where I is the equivalent functional and k comma subscript x is first derivative of k with respect to x. Similarly, t comma subscript x is partial derivative of t with respect to x. Similarly, k comma y, t comma y. Where t comma y is partial derivative of t with respect to x and t comma y, t comma x is partial derivative of t with respect to x, t comma y is partial derivative of t with respect to y. Note that the second integral is evaluated only over S2, the part of boundary over which natural boundary conditions are specified. If you recall, S1 is the part of the boundary on which essential boundary conditions are specified, and S2 is the part of the boundary on which natural boundary conditions are specified. So, the second integral needs to be evaluated on the part of boundary over which natural boundary conditions are specified, and this is the equivalent functional for the boundary value problem that we noted, and this needs to be verified whether this is the functional for the given problem or not. So, here we will be verifying that, and this procedure can be adopted for any other kind of problem where equivalent functional is given for a particular problem, and whether somebody, if somebody is interested in verifying whether that given functional is corresponding to a particular problem or not, the procedure is going to be similar. So, to verify that indeed the equivalent functional which is given in the previous slide is correct functional, we must show that the first variation of this I is 0 when the boundary value problem is satisfied. So, equivalent functional is given, so we need to check whether variation of I is equal to 0 or not. If it is satisfied, then it is going to be the equivalent functional for the given problem, and this can be done by following essentially the same steps as those for those used for one dimensional problems, which we already did. So, first step is we need to take variation of I, equivalent functional is given. So, variation of I can be written like this by using variational identities that we learnt when we started out with this variational approach or Rayleigh method in the earlier lectures. Now, in this equation, interchanging the order of differentiation and variation in the first two terms, because order of differentiation and variation can be interchanged. So, interchanging order of differentiation and variation in the first two terms, we get this. Basically, what we did is variation of derivative of t is written as derivative of variation of t, and now we need to look at what is called Green's theorem to further simplify this equation. So, now let us look at two formulas or two identities to simplify the first two terms. So, these are the two identities: integration by parts in 2 dimensions, which is also called Green's theorem, integral u times partial derivative of v with respect to x integrated over a can be written as minus v times partial derivative of u with respect to x integrated over a plus u times v times x component of unit outer normal to the surface integrated over the surface. And similarly, we can write the second equation also, which is u times partial derivative of v with respect to y integrated over a is equal to minus v times partial derivative of u with respect to y integrated over a plus u times v times y component of unit outer normal integrated over surface. So, using these two formulas or two identities, the previous equation, the first two terms of previous equation can be further simplified. And when we apply integration by parts on the first two terms, we get additional surface integrals. If trial solutions are required to satisfy essential boundary conditions, then variation of t is equal to 0 on the part of boundary over which essential boundary conditions are specified, and this is one of the fundamental requirements which we already looked at in the earlier classes when we started out learning various steps of Rayleigh method. So, to simplify, this variation of I equation, further we apply this condition, since boundary S comprises of S1 plus S2 and on a S1 variation of t is equal to 0, because S1 is the part of boundary over which essential boundary conditions are specified. So, based on this requirement, this equation of variation of I can be further simplified. Therefore, assuming admissible trial solutions, the previous equation of variation of I simplifies to this, which can be further rewritten in this manner. And if you see the first part of the equation, the integrand or the first integral is nothing but the given differential equation, which needs to be equal to 0 over the domain. And if you see the integrand of the second integral, it is nothing but the natural boundary condition that is given, which is equal to 0. So, the boundary integral is 0 for natural boundary condition, the domain integral is 0 if the given or the governing differential equation is satisfied. Therefore, using admissible trial solutions, variation of I is equal to 0, and which verifies that the given or the equivalent functional, that is we started out with, is the correct functional for this particular two dimensional general boundary value problem. So, we got equivalent functional for the given general two dimensional boundary value problem. If we want to derive finite element equations, we need to substitute finite element approximations of t, finite element approximations of t and derivative of t in terms of finite element shape functions of the element that we choose. So, next step, if one want to derive the finite element equations, is to look at how to derive element shape functions. So, we will be looking at triangular element, simplest two dimensional element, 3 node triangular element, how to derive shape functions of that element, so that we can express trial solution and derivative of trial solution in terms of finite element shape functions and nodal values before we derive the element equations. Once we have those things, that is finite element approximation of trial solution and derivative of trial solution in terms of nodal values or nodal parameters and finite element shape functions, we can get the element equations for that particular element. So, triangular element for general two dimensional boundary value problem. Placement of nodes. In finite element formulation, the trial solution is expressed in terms of unknown solutions at the nodes, and this is what we also observed when we are looking at one dimensional problems. For one dimensional line elements, nodes are required at the ends of element, at the ends of the element for assembly considerations. Similarly, or similar considerations for two dimensional problems require nodes at least at the corners of the elements, and extra nodes can be placed along sides or the interior of an element. Thus, minimum number of nodes required for triangular element is 3 at the 3 corners. A typical triangular element with 3 nodes is shown here, and if you see the local node numbering is in the counterclockwise direction, which is shown or indicated by the arrow, and the global coordinates of nodes 1, 2, 3 are also indicated in the figure, and the unknown solutions at the nodes, at the 3 nodes T1, T2, T3 is also indicated. And now we need to derive element shape functions for this 3 node triangular element. Since there are 3 nodes, trial solution must have 3 parameters, that is, we need to start with a polynomial having 3 coefficients. A linear polynomial in 2 dimensions satisfies this criteria. So, trial solution T is assumed to be a naught plus a1 x plus a2 y, which can be written in matrix and vector form as 1 x y put in a row vector, a naught a1 a2 put in a column vector, where a naught a1 a2 are unknown coefficients, and this is, if you recall, this is the procedure that we are adopting here is similar to what we did for one dimensional 2 node element or 3 node element. We started out with, for a 2 node line element, what we did is we started out with u is equal to a naught plus a1 x, and then we obtained 2 equations to solve for a naught a1 by substituting x is equal to x1, u is equal to u1 at x is equal to x1, u is equal to u2 at x is equal to x2. By substituting these, we obtain 2 equations. We solve these 2 equations to express a naught a1 in terms of the nodal values, and once we got a naught a1, we back substituted a naught a1 into u and group the terms containing u1 u2 separately, and whatever is coefficient of u1 and whatever is coefficient of u2, that is, those two are the shape functions for node 1 and node 2, n1 and n2. So, that is the procedure that we adopted when we are deriving shape functions for 2 node line elements. Similar procedure we adopted even for 3 node line element. 2 node line element is linear element, 3 node line element is quadratic element in 1 dimension. So, similar procedure we will be adopting here. So, to start with, to derive the shape functions for 3 node triangular element, the trial solution is assumed as T is equal to a naught plus a1 x plus a2 y. Now, T value at node 1 is T1, to express trial solution in terms of nodal variables or nodal values, we apply this condition at node 1 T is equal to T1 and x is equal xy, x is equal to x1, y is equal to y1. Similarly, at node 2 T is equal to T2, x is equal to x2, y is equal to y2, at node 3 t is equal to t3, x is equal to x3, y is equal to y3. So, by using these conditions we get 3 equations, and we can solve these 3 equations for a0, a1, a2. To solve these 3 equations we can put them in a matrix form in this manner. The coefficients can be expressed in terms of nodal variables by inverting 3 by 3 matrix comprising of the coordinates of 3 nodes of triangular element. So, a0, a1, a2 can be obtained by inverting a 3 by 3 matrix consisting of coordinates of nodes 1, 2, 3. In this manner, and if you notice, inverse of the matrix 1 x1 y1, 1 x2 y2, 1 x3 y3, is not possible if 2 of the nodes are, is not possible if all the 3 nodes are in the say along or lying along the same line. So, that is one of the requirements, that is a 3 node triangular element or a triangular element in which all the 3 nodes are almost collinear is very bad shaped element, because in such a case inversion of this matrix is not possible, or inversion of this matrix is difficult. So, that is on the side note. Now, by carrying out the inversion of the matrix and multiplying with T1, T2, T3, we can get this equation where A is area of triangular element, and F1, F2, F3, B1, B2, B3, C1, C2, C3 are defined. So, we now expressed a0, a1, a2 in terms of T1, T2, T3. So, now substituting a0, a1, a2 back into the equation that we started out with, T is equal to a0 plus a1x plus a2y. Substituting the polynomial equation, we get the trial solution in terms of nodal variables or nodal parameters. So, substituting a0, a1, a2 back into the equation, T is equal to a0 plus a1x plus a2y, we get this equation, which can be compactly written as n transpose D, where n is a vector comprising of shape functions n1, n2, n3, D is a vector comprising of nodal variables or nodal parameters or nodal values T1, T2, T3. So, where n1, n2, n3 are the required shape functions, and they look like this in terms of F1, B1, C1, F2, B2, C2, F3, B3, C3, where F1, F2, F3, B1, B2, B3, C1, C2, C3 are all defined in the previous slide. So, since these all F's, B's and C's are dependent on the coordinates of the nodes of 3 node triangular element, this can be easily computed once the coordinates of nodes are known. And if you see n1, n2, n3, these are linear in terms of x and y. So, that is why 3 node triangular element is also called constant strain triangular element, since n1, n2, n3 are all linear in x and y. Derivative of n with respect to x, derivative of n, all these n's with respect to x and y is going to be a constant. So, that is why 3 node triangular element is also called constant strain triangular elements, constant strain triangular element or CST. So, T can be written as n1 T1 plus n2 T2 plus n3 T3. So, the derivative of trial solution T with respect to x and y can be written like this. You can see derivative of T with respect to x is a constant, because B1, B2, B3 are all constant, and T1, T2, T3 are the nodal parameters, and A is a constant which is area of triangle. So, finally, derivative of T with respect to x is constant. That is why this element is called constant strain triangular element, and similarly derivative of T with respect to y is constant, and it is going to be a function of C1, C2, C3, and each of these can be compactly written as Bx transpose D, By transpose D. So, now we derived element shape functions for 3 node triangular element, and also we expressed trial solution and also derivative of trial solution in terms of finite element shape functions and derivative of finite element shape functions, and the nodal parameters or nodal values. Now, we can plug in all this into the equivalent functional and get the element equations if we decide to use Rayleigh-Grigg method. And we can also adopt Galerkin criteria to derive the element equations. So, what we will be doing is we will now look at Galerkin criteria to derive element equations for the same problem, for the same two-dimensional, for the same general two-dimensional boundary value problem. And now let us recall, this is the problem that we are looking, this is the differential equation. We need to solve over domain A subjected to the boundary conditions. These are the boundary conditions. And also Galerkin criteria for this particular problem, Galerkin criteria corresponding to the given boundary value problem can now be written like this. Galerkin criteria is multiply given differential equation with a weight function, integrate over the problem domain, equate it to 0, and if we decide to use finite element method in conjunction with Galerkin criteria, weight function is same as shape function, and if it is a 3 node triangular element, there are 3 shape functions. So, I takes values 1, 2, 3, and here the first 2 terms inside the integral can further be simplified using integration by parts in 2 dimensions, that is the Green's theorem that we already looked at. So, now let us once again look at those identities or the formulas. So, these are the 2 formulas that we looked at earlier. We will be using these 2 formulas to simplify the previous equation further. So, applying integration by parts on the first 2 terms of the previous equation, first 2 terms inside the integral of previous equation, we get this equation, and I takes values 1, 2, 3. So, further we can write the previous equation like this, writing all the 3 equations together in matrix form, we get this one. And if you see the boundary integral, it needs to be evaluated over S2, that is the part of the boundary on which natural boundary condition is specified, and this equation can be rewritten in this manner. If you compare these 2 equations, you can see the first equation, in the first equation the boundary integral needs to be evaluated over S2, whereas in the second equation boundary integral, it is written as to be evaluated over the entire boundary. And why this is written like this is because the boundary S is equal to S1, the part of the boundary on which essential boundary condition is specified, and part of boundary on which natural boundary condition is specified S2, and the integral value over S1 is unknown, since along S1 essential boundary conditions are specified, and also this term, the integral over S1, as we will see in a while, it is going to be it is going to show up as a reaction term in the element equations, and which we also observed when we are deriving element equations using Galerkin criteria for one dimensional problem. So, further explanation on this integral, which is over S2 the first equation, is replaced with integral over S in the second equation. Further explanation on this can be explained like this: the boundary integral can be split into S1 and S2, that is this integral, which is integral over the boundary S, can be written as integral over S1 plus integral over S2, and integral over S1 is unknown because essential boundary conditions are specified. However, as was the case for one dimensional problems, there is no need to evaluate this, or there is no need to evaluate integral over S1, since the corresponding nodal parameters are known, essential boundary conditions are specified, and the equation containing these terms can be removed from the system before solving for unknown nodal parameters. And this is what we did even when we are deriving the element equations for one dimensional problems. Thus, integral over S1 can be ignored from the element equations, and the integral over S2 can be evaluated using natural boundary conditions. So, this is the reason why the integral over S is replaced with integral over S2 in the second equation. And now this integral on the boundary, during assembly process the boundary integral term from adjacent elements cancels as long as all surface integrals are evaluated in a consistent manner. To understand this statement, let us consider the case when integrals are evaluated by moving counterclockwise around elements like these two elements. So, what the statement says is, during assembly process boundary integral term from adjacent elements cancels as long as all surface integrals are evaluated in a consistent manner. That is, for all element either boundary integrals are evaluated by moving in the counterclockwise direction or clockwise direction. In the figure, for demonstration, the integrals are evaluated by moving in the counterclockwise direction. So now let us consider evaluation of boundary integral for each of these elements along the edge 2 3. So for one of the element integration is from 2 to 3, for the other element integration is from 3 to 2. The common edge between two elements will get integrated from two opposite directions, resulting in same integral but with opposite sign. One integral is evaluated from 2 to 3, other integral is evaluated from 3 to 2. So when we add these two integrals, they cancel each other because they have the same value but with opposite sign. Thus for all interior elements, surface integral term can be ignored. This argument is valid only when we have exact solution, that is the integral value coming from each of these elements is same, but when we are using finite elements, we are after approximate solution. So for approximate solution there is a residual term, however it is ignored, so that a solution for the remaining unknowns can be obtained. For linear element this is always, for linear element there is always a discontinuity of slope no matter how small the element size is. Magnitude of this residual can be used as an indicator of quality of approximate solution. So whatever is mentioned, that is during assembly process boundary term from adjacent elements cancels, this is in a way is not going to satisfy 100%, since we are trying to find approximate solutions, but even though it is not satisfied, we are going to ignore that, and the magnitude of the residual can be used as an indicator of the quality of approximate solution. So now let us look at how to simplify further the boundary integral term using the specified natural boundary conditions. The integral over S2 is this one, this can be evaluated using natural boundary condition, and now let us see what is the natural boundary condition that is given. Natural boundary condition is stated as this one, kx times partial derivative of t with respect to x times nx plus ky times partial derivative of t with respect to ny is equal to minus alpha t plus beta. So substituting this into the integral, it can be simplified in this manner, and substituting the finite element in terms of finite element nodal values and shape functions, it can be further simplified in the manner shown in the equation. So substituting this integral in terms of finite element shape functions and nodal parameters or nodal values into the earlier equation, the complete element equations can be written as kx plus ky plus kp plus k alpha times d, where d is the vector comprising of nodal parameters or nodal values, is equal to RQ plus R beta, or it can be compactly written as KD equal to R, where Kx, Ky, Kp are defined, and all these integrals can be evaluated using numerical integration, or they can be evaluated in closed form if the integrand is not complicated. So, this is how Kx, Ky, Kp are defined, and rest of the terms K alpha is defined like this, which needs to be evaluated over surface on which on which natural boundary condition is specified. R beta again boundary on which natural boundary condition is specified. RQ is a domain integral, and these evaluating all these quantities we can get element equations for a 3 node for the 2-dimensional boundary value problem, adopting once we use shape functions corresponding to and trial solution corresponding to 3 node triangular element, we get element equations for 3 node triangular element. And please note that this K alpha R beta are added only for those elements for which natural boundary conditions are specified. If there is no natural boundary condition specified, these need not be evaluated. Equations associated with essential boundary conditions must be removed from global equations before the solution, and in these equations we need to substitute triangular element shape functions to further simplify these equations to get element equations for 3 node triangular element for 2-dimensional boundary value problem, which we will be seeing in the next class.